Hi, did you guys have a good weekend? Enjoy the nice weather? That was nice. I did. I took several walks, campfire. It was good. I'm the kind that I like campfire smell, so I haven't washed those clothes yet. I'll probably go home and but that's me. Do you guys have any questions about anything? I know you normally don't, but I like asking because, every once in a while. I didn't like those classes where the teacher just started rambling on and I forget that, oh yeah, I had that thought. I was curious. So, yeah, Glenn? That's correct, yeah. We started this unit, but just Friday. And so I'm finishing chapter 19 today. So we hadn't even finished a chapter. So Wednesday will be 20, and Friday will finish 20. So this next weekend, you'll have chapters 19 and 20, which you've already had access to. So yes, there was no homework, which is fine, because you guys had your exam and superhero paper review, so it worked out, sort of. Anything else? Okie doke. Then I have 2 questions I'd like to ask you. Clickers. All right. Here's the first one. Open when you guys get all your stuff out and logged in, signed in. We introduced frequency and period terms. See if you, from a question, can determine what that is, since I ask you that a lot in the homework. Now, these aren't special razors that only Europe has. It's just, do you remember that when we plug things in here, I don't know if it came up, but the frequency of our alternating current in the United States is 60 hertz. Now you know what that means. It changes directions 60 times every second. In Europe, they use 50. And yes, if you're paying attention, I gave you half the answer. That is one reason, well, I'm stalling a little for people to sign in the first time. Different countries, they have different plugs. The stuff you have here, if you go international, it doesn't necessarily work. Not just because you can't physically plug it in, but because if you did, they might run on a different voltage. And it's giving a different amount of energy per charge. Remember, that's what voltage is? And so you could fry your equipment. But also, if your equipment's designed to run at a certain frequency, and you take it somewhere else where they're providing a different frequency, that could fry it also, or it wouldn't work. So this is another reason. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 68% for number A, you're correct. So yeah, the frequency is 50 hertz because it's 50 vibrations per second. What if it was every 2 seconds? What would the frequency be? 25, right. 50 divided by the 2. And the excuse me, period is the inverse of that. If it goes back and forth 50 times every second, how long does just one cycle take? Well, 1/50th of a second. So that's the period. Questions? And I'm serious about this because if you can't figure out what the frequency and period are out of a lot of these questions, you won't be able to answer them. Okie doke. All right, wave interference occurs for what? That was what we covered at the end. That superposition, constructive and destructive, in phase, out of phase thing. What's it apply to? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Oh, bless you. All of these. Correct. Those are the two I wanted to ask you at this point. Yeah, interference works for all kinds of waves. We've been talking about waves in general for now. We're starting with sound, but I keep throwing in light. It works with water. And I'm going to do an example here in just a second. That's what this big one is. So yeah, this interference, this superposition of waves, that works for all waves, anything you can think of. Again, matter doesn't like sharing space. We can't sit in the same chair. But if we were a wave, we could pass right through each other. Let's do this demonstration now. So this is two speakers. I'm going to send sound out of this one and this one at a certain frequency. It is 1100 hertz. You know what? Let's do it. This vibrates 1,100 times every second. That's the frequency. So the period, 1/1100 seconds. What's the speed? How fast is it going? Okay, good. We have wavelength times frequency. So if we knew the wavelength, that would be good, but we don't. So yeah, if half of you are thinking, oh yeah, we got to calculate that, blah, blah. This is one where we reason through what is vibrating at 1100 hertz. What's vibrating at 1100 hertz? The speakers do, that's for sure. That's one. That means these are they push this way, and then they go back, and they're doing. So if we start forward, or let's just start here. I'll exaggerate. There's one cycle, 2 cycles, 3 cycles. So yeah, it vibrates at 1100 times a second. If they push the molecules in front of it, what do the molecules do? They compress and then expand, compress, expand at 1100 times a second. What do they do to the molecules next to them? They bump them. And so two things are vibrating at 1100 hertz. The speaker, which then pushes the air. So the air is vibrating at 1100 hertz. It's the wave. I heard somebody very quietly mumble it, but then afraid to say it again. The wave, you could say, is vibrating at 1100 times a second. The wave. Even though it's not a transverse wave, it's a longitudinal wave. I'll show an animation in a moment. How fast does that wave travel? That's what we need to know. You might not know the value, but we give it a term. The speed of sound. Yeah. It's traveling at the speed of sound in air. Which we went over last time. I didn't expect you to memorize this, but it's about 340 meters per second at room temperature. Or is that at 0? It might be at 0. Whatever, we're going to use that. So if it travels 340 meters per second, that's how fast this vibration will travel in space to get to you. It's still wiggling at 1100 hertz, but the disturbance, the vibration, the wave itself will travel at 340 meters per second. So if we now know the frequency and the velocity, let's figure out the wavelength. Figure it out. What do you guys get? Let's see how big this wave is that we hear. All right, wavelength is velocity over frequency, if you just rearrange it. The velocity is 340, the frequency is 1100. I didn't pre-do this. Anybody with calculators out there? And meters, since we use meters per second and hertz cycles per second. So it's about a third of a meter. That's about, here's a meter. So a wave is about that long. Ironically, roughly, that size. I didn't plan that. So we can picture it. So that's the size of a wave that comes out of this speaker and the same size that comes out of this one. Well, now you got two waves that are going to come at you. You got one from here, travels a certain distance to Kara's ear. You know, it's going up and down, up and down, up and down, or it's together, apart, together, apart, together, apart. Well, then this one does the same thing, but it has a different distance before it gets to your ear. And so by the time they get to your ears, they could be in phase or out of phase. One could be smushing while the other's spreading. One bump up while the other bumps down. So I'm going to change the distance to your ears. So we don't have to talk over it. What did you guys notice? Did you hear it? Yeah, it got a little louder, a little quieter. It wasn't perfect destructive interference because they bounce off the walls and come at you from different directions, and so they couldn't all cancel out. But I hope you at least heard a dip where they're partially getting canceled out because the distance changed. Now they're out of phase. One up, one down. I actually prefer half this frequency. Let's go to 550. There we go. Try it again. Some people notice it if the change is quicker. They're not changing. They're emitting the same frequency the whole time. But what we hear, the amplitude seems to change. Interference affects the amplitude because they either add together or cancel out, partially or wholly. Yeah. Sort of. It's sort of similar to resonance. Let's jump to that. Will you help me, Stephen? Will you come on down and help me with this? Because resonance has to do with interference and superposition. But it's in and out of phase, and it affects amplitudes. But let's discuss resonance a little. We'll do it more later this week. But here's a spring. All right. And the source of all waves, source of all sound, is a vibration. So get it vibrating, Stephen. You're natural. And most people naturally tend to create what's called a standing wave, which he had there for a moment. What happens is, there it is. How many bumps do we see? 1, 2, 3. Is there 4? That's a standing wave. We've hit a resonance mode for this spring. The spring naturally wants to vibrate like this. And so he's driving it at the same frequency it wants to naturally vibrate at. That's resonance. So what's really happening is, he'll take a break. If you just send one pulse, you can see it. The incident wave goes, and then it reflects and bounces off him and comes back and keeps doing that. Well, if you keep driving like Stephen was, is that one 4? Then the wave that goes that way And the waves that are coming this way are superimposing on top of each other. And they're always in phase at this resonant mode. So the wave going this way and the wave going this way, they're both up at the same time. You can vibrate at some funky frequencies, like kind of like this. And you can see waves traveling, but they kind of, sometimes they add up, sometimes they cancel out. So when you use interference, this superposition, to get a resonant mode of something, it can create a standing wave. Can you get 3 bumps? There it is. There it is. There's another resonant mode. And it's called a standing wave because it looks like the wave isn't traveling left and right. It just looks like a bump is going up and down. The spots in the middle, like here-ish, sorry for messing it up, those are called nodes. Nodes. They look like they're not moving. They're a place of no displacement. And the bumps, like here, up, down, those are called antinodes. That's where it's maximum displacement. Now, how did you get 3 versus 4? What did you have to change? Yeah, how fast. That's the frequency. Did you go faster or slower? Slower frequency got the 3 bumps. Can you see the distance between bumps is greater? What's that called? Distance between bumps? From one crest to the next crest? It's a wavelength. That's the distance it'll go up. It travels in one cycle. How big the bumps are, the amplitude. All right, can you get 2 bumps? There's 1 bump. Stick with that one. This is the fundamental. This is the slowest this spring can get. This is the lowest resonant mode. 1 big bump. What's the size of the wavelength? Length of what? From me to him, we can fit 1 bump in between us. How many bumps do you need for a wavelength, a complete cycle? 2. You need the up and the down. So what's the wavelength here? It's twice the length between us. If you could visualize the whole wave, yeah. Now you want to go for 2 bumps? If we can get 2 bumps between us, then the wavelength will be the distance between us. He's changing the frequency again. Oh, that changed the amplitude. So go a little faster. A little faster. A little more. You're almost there. Are you tired yet? It gets tiring, though. There it is. You can see it's vibrating faster than 1. The frequency has increased, and the wavelength has decreased. It's now the distance between us. You could time the cycles. 1, 2, 3, 1001, 1002, 1003. You can see it go up and down. So you could get the period, and thus the frequency. You know the wavelength. We could determine what the speed of sound is, or the speed of the wave is in this spring, couldn't we? Because we can measure the wavelength, and you can time it for the period. From that, you get the frequency. All right. Okay, you take a rest, and just for fun. What? That'd be a really, really high note. Because you can see it's going faster, but the wavelength is shorter, and I lost it. But there you go. Anyway, thank you for helping with that. Those are standing waves. They, again, occur because of interference, the waves reflecting back and forth. All musical instruments create standing waves somehow. And those different resonant modes, you can get different notes. You can change where those resonant modes occur, too. How would you do that? What if you wanted a different frequency to hear a different note? 1, just vibrate it faster. That's the easy way. So if you're playing like a bugle, you can go, that determines the frequency. Or you can do, as you blow, it's vibrating faster. So that would be a higher note. What's another way to get a different frequency, a different note? You can change the length of the spring or the string. Yeah, if you make it shorter, generally they vibrate faster. And there's one other way you can do it. So you can change the frequency, you can change the wavelength, or change, yeah, Kira? The width? That's the same idea, yeah. That would essentially change the material, like he said. What if we replaced that spring with a different spring that had a different springiness? Elastic constant. For those of you who know Hooke's law, spring constant. Yeah, then the speed, the velocity would be different that the wave travels. If you vibrated exactly the same frequency, but if the sound, the wave, can travel faster now through the material, what happens to the wavelength? If this increases, the wavelength increases. So you can change the note you get by changing any of these. This one, you just vibrate at a different rate. This one, you can change the length of the horn or the tube or the string. And the wavelength that gets set up is a different size, vibrating at a different rate. For example, trombone. If you make it long, then you can get a big wavelength that vibrates at a lower frequency. Because we're still dealing with the speed of sound in air there. That's the wave in air. But a guitar, you have different strings. Different tensions affect the speed they travel. Let's take a guitar while I'm on it. They're all about the same length. So the wavelength is about the same on a guitar. But if you tighten one, you know, the pitch goes up. That's because as you increase the speed that can travel through the string by changing the tension, it'll vibrate more quickly. And you hear a higher note. But that's that nice relationship between those. Yeah. Yeah, as curious, a different mass. That affects that speed. Because, yeah, essentially on a guitar, they're all made out of the same material. I should say spring or steel, usually. Or you could have nylon. But they make different thicknesses, which changes their mass, and thus their inertia, how fast they want to respond. Something generally more massive will be a little more sluggish because of that inertia resisting the change. And so your thick guitar strings vibrate more slowly and make the lower notes for the same wavelength. Because sound travels more slowly through them, and vice versa. And generally longer instruments have bigger wavelengths, which vibrate more slowly. So your tubas, compared to a piccolo, really short. And you're essentially just changing the length that the wavelength sets up when you're playing a flute by covering and opening the holes. If you close them all, the effective length is essentially the length of the flute. I'm approximating because there's other things going on. But if you open this hole up, whoop, oh, now that's the effective end. And the wavelength's shorter, and you get higher notes. Anybody play the flute here? Oh, there's usually always one. So that's how they interplay. That's how you can find various things. You can time things. Back to there. Again, if we timed the period of this wave, the time it takes to go up and back down, you got the period. Measure the length, say from here to here, that's one wavelength. Or from here, okay, to here, that's the same wavelength. Well, from this you have the frequency, from this you have the wavelength. We could figure out the speed of that wave traveling back and forth. And then you change to a different spring, you could get a different velocity. Let me show you an animation. I have too many open because there were several I could show you. There's the first one I want. So an animation of a longitudinal wave. We did it with a green slinky before, but you can kind of see it there. So you look at this spring, it goes this way, and then it smooshes it and goes this way, but then it comes back. But the wave looks like it's traveling all the way through it. Come back to this one, it's going through it. Look at it from a different angle. That's how sound travels, a longitudinal wave. So these speakers are pushing the air and compressing it, and then this air right here just goes like this, back and forth in spot, but the wave travels to you. So this demonstration with the speakers looks like kind of like this. Here's the two speakers, one there, and if you're sitting right here and you're watching your surround sound high definition movie, here come the wave fronts and boom, boom, boom. They both peak at the same time when they get to you. Think of these as wave crests. Think of this green one as when that wave is up, 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 and it gets to your ear. So up, down, up, down, up. You see what I'm getting at? At the purple, you can do the same. The wave from this speaker is up, 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 and it gets to your ear the same time the green one does. And so they're in phase. Do you see the visual here? By the time the green wavefront and the purple wavefront get to you, they're in phase. And this is what you would hear down here. Now let's just shift over, let's see, right here, where my arrow is. What do you think you'd hear there? More green, less purple? Right along this line? Any other votes? Well, let's find out. Let's see if I can move. You have a vote of the same? Why do you guys say what you say? Closer to the green? They do travel at the same speed, yes. It will take longer to get to you. That's true. That's true. So, Glenn, why do you say it'd still be the same? Same ring on the circumference. Well, let's see if I can move it over there well enough. That's the thing that disappears. All right, they come. So look at that green one. Here comes the first green one. And you're right, Stephen, it hits you first. You hear it. Oh, but now they both get to you in phase, and it's just as loud. So that initial wave front gets to you first, and it's not as loud because you're closer. But that happens real quickly, 340 meters per second. So essentially, we hear the same thing. That's what's going on here. Now, if I move these, or you guys could move, let's move to in between. Let's go here. Here come the waves. They're still going to, the green one's going to pass, and the purple one passes, but then green, then purple, then green, then purple. Green's up, purple's up. Green's up, green's down. Green's up, green's down. So they're out of phase, mostly. And look at the bottom there. It won't be as loud. So it does matter for certain frequencies, certain wavelengths, the position of things. And that's why you guys would hear this change as I change the relative distance between your ears. Questions? All right. While I'm here, let's do this one. So here's these two waves. If they interfere, they add up, because this one's up, that one's up, so you get twice the amplitude. So what's the amplitude here? Yeah, about a half. Here, half. You add them together, you get one. Let's change the phase. Watch the blue, the top upper two. I didn't change these guys as amplitude, but when one's down, the other one's up. And see how it's kind of canceled there? Phase change. Let's right there. It's completely destructively interfering. That's interference. Superposition. They're superimposed on top of each other, and in this case we have perfectly destructive interference. Nope. All right, let's do this. Whoop. Here's some water waves. and they're traveling by like ripples in a pond, or a boat goes by and you're sitting on the dock, and you can count the number of crests of those waves, ripples that come past you. Or you're observing this little leaf, or you're a fishing bobber who likes to fish. If you count how many times it goes up, back up, what are you measuring? The time it takes to go up, 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 up. Yeah, you get the frequency, the rate, and thus the period. One or the other. Most people would, in this case, if you're sitting on the dock watching, you get the period. You could time it, 1001, 1002, if it's a second. And from that you can get the frequency. What's the wavelength? Well, that's the distance from one crest to another. Let's see if I can, there. From this crest to that crest. So you could eyeball the distance between waves as they come. So even if you're at the beach, you're seeing them come in. It's a big wavelength, but you could get that. Look, if we change the wavelength, we make it bigger, it still goes up, down, up, but the waves don't seem to be, the frequency is not as fast. It doesn't go up and down as quickly because we adjusted the wavelength. How fast is the wave traveling? I didn't change that. That's the speed it's traveling in the water. What if I make the wave travel faster? What do you expect to happen? Frequency goes up? Let's see. Yep. If the wave comes by you faster, because it's moving faster, then yeah, each of those up and downs is going to be more quickly, happen faster. Increased frequency. But we didn't change the wavelength. So my suggestion, when you're working out some of these homework problems and or on the test, you have three variables: velocity, wavelength, and frequency. It's helpful to realize usually which one is not changing, or it'll mess you up. If you adjust one, something else has to change. Which one is it? Confuses a lot of students. Well, if it's still traveling through air, and we didn't change the air, then the speed of sound is probably the same. Or if it's traveling through water, and we're still in water, we probably didn't change the velocity. But if we change the material by making it thicker, warmer, or just completely different, then the velocity probably changed. So that is my little tip or help out for that. Let's do, actually, this one. Here's a little spring slinky on here, and I can rotate it. I can turn it around and around. So if I put it on the overhead projector, you can see me turning here, going in a circle. But what's it look like happens? Looks like there's a wave traveling to my left. You can watch one of those crests and you can see it move. That's the wave velocity. If we could get the distance and the time. But each individual little spring is just going around in a circle. It's not moving left to right. You get an idea of the wavelength. That's the distance between them. From here to, it's easier up here. From here down, back up. That's a wavelength. A wavelength. Just to help you picture a wave, since we're dealing with them a lot. Now, if I turn faster, besides it wiggling more, you can see the wave speed increase. The peaks go by faster. But I didn't change the wavelength. So what else changed? I changed the velocity. The wavelength's the same. The frequency. Yeah. Look at the same spot. Watch this spot right here. Not the spring, the spot on the screen. I know it'll be a little difficult, but next, next, next. And if I go faster, next, 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 you can see it passes by it more frequently. Hence the frequency increased because it's traveling faster. To change the wavelength, I'd have to stretch this like that and do it again. Here's another fun way to do this interference stuff. I have a overhead transparency with some different wave crests. You can think of the blacks as when it peaks. This one's identical to it. So if I take the two and superimpose them exactly on top of each other, you get that. Now let's think of these as those speakers. If I separate them, you get your two sound sources. This could be the sources of any wave. Light, two stars in the distant galaxies, two pulsars emitting waves. Well, if you're standing right here and you got your telescope or your ear, it looks like they're out of phase. One's up, then the next. Up, down, or actually it'd be like this one's up, then the other one's up. Up, up. They alternate. So if you're in this line of the path, they'd be destructively interfering. But if you're in this line of the path, look, they're together, in phase. It'd be louder there or brighter. Works with any waves. What's fun is that you can change the distance between the sources. All right. And now the gaps get closer together, tighter. As they get closer together, now you got a big range where they're constructively interfering and a bigger range where they don't. And again, this works for all kinds of waves. If these were water ripples, sound from the speaker, or light. I'll show you a demo later when we get to the chapter on light, how they can interfere. All right, 10 minutes, regroup. So we got standing waves, all that stuff. Oh, I did it when I was up there. So let me draw a picture. We send an incident wave in like I did to Stephen, and then it bounces back. Draw it as a dotted line because they don't happen at the same time. It's going, and then it reflects back. Then you get this standing wave. It just looks like this bump is going up and down, up, down, up, down. Well, these spots, you'll need to know, are called the nodes. It's in your book, but I wanted to make sure. They're the places where they're along the equilibrium position, and they don't appear to be displaced, hence a standing wave. These spots are the antinodes, and they're the places of maximum displacement, where it moves the most. So in this standing wave, this resonant mode of this spring, at this frequency, it likes it. We're driving it at the frequency it naturally wants to resonate at. That's called resonance. We get this standing wave mode, and we have 4 nodes and 3 antinodes. You know, if we switched it and he started vibrating more slowly, then we got one big one at one point, and then it bounced back, and then bounced back. Where you only have 2 nodes and 1 antinode. It's a different resonant frequency, a different standing wave mode. And that's how you can get different notes on the same guitar string or on a flute or something. Alrighty. What? Standing waves. They look like they're standing still. Imagine if Steve and I could do this at a much higher frequency where our eye couldn't keep up. We would just see like this big bump over here because it's going up and down so fast. It would just look like there's a bump here and a bump here and a bump here, up and down. It's just we were going slowly so we could follow it. Now what if a sound source were to move while it was emitting waves? Like a what? Fire truck, yeah. It's got its siren on, producing a certain frequency. These wave crests are going out, reminding us of that it's up or down. Well, if the source is moving at a certain velocity, and the waves themselves are traveling through, in that case, air from a fire truck at a certain velocity, you can catch up with the wavefront. And what do you think would happen if I'm the fire truck and you guys are sitting there and I'm putting out a frequency? Boop. When I do that, you get a wavefront. You know what? I got an animation for this one. Save time of me instead of me sounding and looking like a dork, which I know you're used to. This one. Jet. Okay, it emits waves. If you're right here, what do you hear? Bump, 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 bump. Every time the wave crest passes by your ear, bump, 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 bump. Now, if this is moving, so the waves still travel at the same velocity, but now the source is moving also. Bump, 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 bump. We're not changing the wave speed, v, but they're passing by you at a higher frequency. The wavelengths appear shorter to you. The fire truck isn't changing, and the jet isn't changing what it's doing, but you perceive it as being at a higher frequency because it physically passes you at a different rate. Do that again. Let's go faster. If you're like right here at the arrow, you don't hear anything, and then bump, 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 and then as it passes you, well, check this out. Bump, 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 bump. They get farther apart. You hear them less often. The period increases between blips. Thus, the frequency goes down. That's the Doppler effect. When the fire truck goes past you, what do you hear? The pitch changes. Not what it emits, but what you hear. It's harder to do There they are. Oh, helps if you plug it in, Adam. Honk the horn as you go by. The Doppler effect. Because you're moving in the same frame of reference as the car, the horn. So you're moving with it. So you don't hear a change. It's like the horn's right next to you. All right, let's adjust that then. Let's get outside the car. Now we're standing at rest relative to the sound source, and here it comes. So as it's approaching you, if you guys are coming together, you should hear an increase in frequency because they're hitting you more frequently. And vice versa as it goes away. Listen for that this time. Higher. Lower. Now what if we switch again? This time, well, you just watch. Maybe if I close them, I won't get as confused. Did I do it again? Okay, memo to me. Label these differently. because obviously outside 1, outside 2, inside 1 doesn't work for me. Okay, here we go. No change. It's coming from this car, the same horn. We're not moving with respect to it, so you don't hear a change. Now, which one do I want? Is it that one? Past the red car that was honking its horn. So now there was relative motion between us. This has nothing to do with the theory of relativity, but you hear the shift. So while I have this up, to help you visualize, that's this. What if you go the speed of sound? There it is. If you go the speed of sound itself, you're going the same speed as the wave fronts. And they all get bunched up right here, and you have a huge pressure difference because each wave front is smushing the air together at the same spot. They're all constructively interfering on that wave front. And you just created a sonic boom. It's the velocity ratio between the jet and the sound is exactly 1 to 1. You're going the same speed. And if I hear nothing, that the arrow, and then boom, you hear a sonic boom. As it passes you all at once, all of those pressure waves add up at your ear as it passes by. That creates a sonic boom. This is a shock wave. What if you go faster than the speed of sound? You actually get ahead of your wave fronts like this. But notice they still bunch up along the front here. And so if I'm at the arrow, nothing, boom, you hear the sonic boom again. So you have to be going the speed of sound or faster to hear the shock wave of the sonic boom. To end quickly, here is a buzzer. Fixed frequency, but if I can move it, have it coming at you and away from you, you should be able to hear the Doppler effect. You hear that wow, wow? So it should be higher frequency when it's coming at you and lower away. Higher, lower. If they're spinning, yeah. Well, we actually detect how fast a star is rotating from this, because this works with light waves too. If the light that's the star, and the light from this side of the star comes at you, it actually gets shifted in frequency. Have you guys heard of blue shifted? Blue has a higher frequency, a shorter wavelength. So it's like the sound getting higher, but for light. This side that's moving away from you, the wave's frequency increases. It's like hearing a lower sound. It gets red shifted. And that difference in how much the light gets shifted tells us exactly how fast it's moving away and towards. And so we can tell how fast something's rotating with the Doppler effect. All right. See you guys Wednesday.